So, Sarah, you're saying categorical data is just as important as continuous?
Absolutely, Jane. We've been mostly focusing on numbers, but real-world data is often a mix. Think about customer demographics. Age is continuous, but what about their preferred shopping method? Or the product category they usually buy?
Right. Those aren't easily expressed as numbers.
Exactly. These categorical features need their own special treatment to be useful in machine learning models.
How do we do that?
One common technique is one-hot encoding. It converts each category into a new binary feature.
Like turning color into red, blue, and green?
Exactly. Each original category gets its own column. If it's red, that column gets a 1 and others are 0.
So if someone likes both red and blue?
Both corresponding columns get a 1.
That makes sense. So, how does this work with our adult income dataset?
Each category for work class, education, occupation, and so on, would be converted to separate binary features.
That sounds complicated.
Well, it's not always straightforward, but understanding these techniques is key to feature engineering.
This process of converting categorical variables is critical for algorithms, correct?
Absolutely, Jane. It significantly affects model performance.
What if there are missing values in a categorical feature?
That's a great question, Jane. We might want to create a special category for missing values or fill them based on the majority class.
So many considerations.
Feature engineering is an iterative process. You test different representations and see what works best with your chosen model.
This feels like a lot of work. So, why is it important?
Well, Jane, getting the right representations can make a huge difference.
Even more important than the parameters of the model.
You got it, Jane. And that's why it's such an important skill for data scientists.
Okay, Sarah, so we've talked about continuous data and categorical. How do we deal with categories within our logistic regression model?
Well, imagine this formula we're using. It's designed for numbers. Masters or private employee aren't numbers.
Right. So, we need a way to convert those words into numbers.
That's where one-hot encoding comes in handy.
Can you give us an example?
Sure. Let's say work class has values like government employee, private employee, etc.
So, we turn work class into a bunch of new columns?
Exactly. For each possible work class value, we have a new column.
Government employee, private employee, etc. How do they get values?
If the person is a government employee, that column gets a 1. The others get a 0.
Wow. That seems pretty straightforward.
It's simple but very useful. If someone is both government employee and a private employee.
Oh, both columns get a 1.
Yes.
So, we take out the original work class column?
Exactly, we only need the new binary features.
So, what if there were many categories? Would that make the data difficult to use?
Not necessarily. The key is that it makes the data more suitable for logistic regression.
Interesting. Is this similar to the dummy variables concept from traditional statistics?
Somewhat, but in machine learning, it's more about representing the categories in a way the model understands.
So, machine learning encoding is different from statistical encoding?
Yeah, there are subtle differences. Machine learning one-hot encoding is simpler. A 1 in a column indicates the feature's category was selected.
This is crucial for making logistic regression work with categorical variables, right?
Absolutely. It transforms the data into a format the algorithm can process.
So if we have education and occupation, we create new features for each value?
Exactly. It adds features but changes nothing about the structure of our model.
What do we do about missing values?
We could create a new category for missing values, or fill them.
Okay, this is getting clearer. Is there a better way, or are there other alternatives?
Absolutely. There are other ways to represent categorical features. Some involve ordinal encoding or more sophisticated ones like target encoding. Each method has its place.
Great. Next, let's talk about the best way to implement this in Python.
Great idea, Jane. Let's move to practical tools.
Sarah, you mentioned loading the dataset. Let's do that now.
Okay, Jane. First, we load the data using pandas. See this code?
Interesting. We're using PD read_CSV.
Exactly. Notice header equals none and our custom column names.
Why header equals none?
Because the file doesn't have column headers.
Got it. What about index_col equals false?
Keeps the rows as indices, important for avoiding confusion.
So, we've loaded the data. Now what?
Let's check the gender column. See, we use .value_counts.
Aha. It's a nice, clean, balanced representation.
Exactly. We've got male and female.
Perfect. Now to encode. How?
We use pd_get_dummies on the categorical columns.
Like what?
Like work class, education, and occupation.
Makes sense. But what about the missing values?
Great question. We'll need to handle those, might involve a new category.
Or fill them, right?
Yeah, that's one approach. Or dropping rows, or replacing it with average/median.
A few options. So, get_dummies is simple?
Very. But think about a column with many categories.
It might cause issues with overfitting, right?
You're spot on. And that's where another method, scikit-learn's one-hot encoder, can be useful for more complex cases.
We have to be careful about that, yes?
Absolutely.
This is a crucial step for the whole machine learning process, right?
Exactly. Validating and preparing data are often the most time-consuming parts.
Thanks, Sarah. This is great.
You're welcome, Jane.
So get_dummies is good for simple tasks, but we need to consider other tools like one-hot encoder too?
Precisely. It's good to have both in your toolbox.
So, encoding categorical data is critical, but we need to choose the right tool based on the dataset's specific needs.
Absolutely right.
Great, thanks.
You're welcome.
Sarah, so get_dummies is a practical way to encode categorical data. Can you explain how it actually works?
Absolutely. It takes your data frame and creates new columns. For example, see how it makes separate columns for workclass_federal_gov, workclass_private, etc., for each value of work class.
Wow, interesting. It's like creating a new column for each category. That makes sense.
Exactly. Notice how the original columns like age and hours per week remain untouched.
Interesting. So, the continuous variables stay as they are.
Right. That's a key point. Get_dummies only deals with the categorical ones.
Okay, so what about that number-py conversion? Why is it necessary?
To feed the data into scikit-learn models, it needs data in a numerical array.
Aha, a fundamental step.
We then carefully extract only the features from age to occupation_transport moving, excluding the target column income for training.
I see. And how do we deal with, missing values like ?
Get_dummies automatically handles those by creating a separate column, but it's critical to recognize and understand how it's encoding.
That makes sense. But could we lose critical information by converting to dummies?
It depends. Sometimes it might lead to overfitting issues if there are a lot of categories.
So, what's the best approach in such situations?
For large categories or situations requiring more complex handling, scikit-learn's one-hot encoder can be a better choice.
That seems like a very useful tool to know about.
Exactly. You always want the best tool for the specific job. What do you think, Jane?
I think that get_dummies is good in simple cases, but the potential for overfitting with many categories is worth remembering. It's good to know that scikit-learn provides another method for more advanced handling.
Indeed, a well-rounded data scientist needs both approaches.
So, understanding these differences in handling categorical and continuous variables is crucial for good machine learning, right?
Absolutely. The preparation phase is critical and can make or break a model.
Thanks for clarifying.
You're welcome. I'm always learning more about machine learning.
Sarah, you mentioned before that get_dummies can cause trouble if the training and test sets aren't encoded the same way. Can you explain why?
Yeah, it's about consistency. If a category like private employee is in the training set but not the test set, then get_dummies generates a different feature structure. It's like they're speaking different languages.
Whoa, that's a big problem. Data leakage, right?
Precisely. The model trained on one set won't understand what's happening in the other.
So, how does this work with numbers representing categories?
Get_dummies treats them as continuous. If those numbers actually represent categorical information, it's wrong.
So what's the better approach, Sarah?
One-hot encoder lets you define which columns are truly categorical.
So how would we do this with our integer example?
Let's see, we could convert that numeric column to strings, then use get_dummies, or use one-hot encoder. One-hot encoder is often better for large datasets, as it handles the categorical encoding directly, which can be more efficient.
So when should we choose which one?
Get_dummies is faster in simple cases. One-hot encoder excels in managing high cardinality features, or when we have a good understanding of which variables are truly categorical.
Interesting. What about missing values?
Get_dummies handles question mark in the training set. The test set must contain the same categories.
That is super important. Any real-world examples?
Imagine a loan application system. Different regions have different rules. Encoding them consistently, whether in get_dummies or one-hot encoder, is vital for accurate predictions.
Thanks for the insights, Sarah.
You're welcome. It's all about understanding your data's nature.
Let's look at an example. Say, some integers represent different job types. Should we treat them as categories or continuous?
Depends heavily on the underlying meaning. Without knowing the ordering or meaning, you probably want to treat them as categories, not continuous values.
Okay, that's crucial.
This is a great illustration that good data preparation really matters in machine learning.
Yes, it's like building a house. You need a solid foundation.
Absolutely.
Sarah, so we've seen how get_dummies doesn't automatically treat integers as categorical. How do we fix that?
We need to tell it explicitly, or we can convert them to strings.
Interesting. So, how does it actually work?
You use the columns parameter in get_dummies to specify the columns you want to treat as categorical.
Got it. What about binning continuous features?
Well, imagine you have a feature like temperature. You can divide that into ranges like cold, moderate, and hot.
So, you're turning a continuous variable into a categorical one?
Exactly. That's binning. And you often use np.digitize to do that.
How does one-hot encoder fit into this?
Well, one-hot encoder excels in transforming these discrete bins, which are now categorical.
Okay, so, to use the example, you've got the temperature.
You bin it. Then one-hot encoder turns those bins into a series of columns.
Makes sense.
You can even do this for features like ages.
What about different binning strategies?
You could have equal width bins or equal frequency bins. Equal width divides the range equally.
What's the problem with using too many bins?
You could overfit. Your model might memorize the training data and perform poorly on new data.
So, what's the best approach?
There's no single perfect answer, Depends on your data.
What are the risks of using too few bins?
You could lose valuable information.
Can you give a real-world example?
Think of customer age. You might bin it into categories like under 25, 25 to 40, 40 to 60, and over 60.
So for binning, are equal width or equal frequency bins better?
Well, it depends on the distribution.
Can you show how one-hot encoder works on bin data?
Let's say we use equal width bins. np.digitize divides data, creating categorical bins. Then one-hot encoder translates each bin into binary columns, ready for the model.
That makes sense. What are the pros and cons of get_dummies versus one-hot encoder?
Get_dummies can be quicker on smaller datasets. One-hot encoder is generally preferred for large datasets or categorical features.
Makes total sense. Thanks, Sarah.
You're welcome.
Sarah, so we saw that binning might not be the best approach for tree-based models, right?
Yeah, decision trees are pretty good at finding splits wherever they help them predict best.
But it seems useful for linear models, though. Why is that?
Binning helps linear models by providing a way to create local trends within each bin.
Okay, but what if we just added the original feature back in?
That's a clever idea. Then the linear model can learn a different slope within each bin.
So, what's the effect of adding interaction terms?
It helps capture relationships between features. Imagine if two features strongly influence the output together.
Wait a minute. Adding these interaction features, could that lead to overfitting?
Absolutely. Too many interactions and our model memorizes the training data.
So, what's the key here? How do we avoid overfitting?
Careful feature selection is key, and regularization techniques. And we need to look at how much interaction information there actually is.
It makes me think of polynomial features, right?
Yes, it's like adding higher order relationships between the features, enabling more complex curves.
So, this whole feature engineering approach, is it just for linear models, or is it more broadly applicable?
While linear models gain a lot, it's a good idea for all kinds of models. Good feature engineering is crucial.
Is there a good rule of thumb? How many interactions is too many?
There isn't a hard rule. You need to experiment and use domain knowledge. If it feels too much, it probably is.
Great point. So, Sarah, what are some real-world examples where this kind of feature engineering would really shine?
For instance, in finance, you might find interaction between different stocks and some measure of economic uncertainty affecting price.
So, the key is understanding the data and seeing what relationships are most relevant.
Absolutely. Even if it feels like too many features, a good model selection process and validation can help us manage that.
That makes a lot of sense, Sarah. It really illustrates how much there is to feature engineering.
It is quite the art form,
Thanks for the insights, Sarah.
Anytime, Jane.
Sarah, you were saying interaction features help linear models learn complex patterns. Could you give me an example?
Sure, imagine predicting house prices. Just size isn't enough. Interaction between size and location matters. A huge house in a bad neighborhood won't fetch as much as a smaller one in a desirable location.
Aha. So we create an interaction feature combining size and location?
Exactly. It captures the combined effect and allows the model to learn a different relationship for different areas.
Interesting. But what about polynomials?
Polynomials, like squaring the feature, capture nonlinear relationships. For instance, if the relationship between temperature and demand for ice cream isn't linear, adding a squared term for temperature can make the model fit the data more accurately.
So, more features, potentially a lot more features. Might we overfit?
Definitely. A model that learns the exact noise in training data is useless on new data.
How do we handle it?
We use techniques like regularization, like penalizing large coefficients, to control complexity. Also, model selection is key. Cross-validation helps us choose the right number of features.
So, it's not just about adding features, it's about adding useful features. Which is better, interaction or polynomials?
It depends. Interaction features are good for capturing multiplicative effects. Polynomials for nonlinear relationships. Sometimes a combination can be best.
My gut feeling is adding lots of polynomial features might add a lot of noise.
True, and it's not always clear which are the most meaningful. There's an art to feature engineering. You use your knowledge of the data, try different options, and evaluate them critically.
So, we need to carefully assess the effectiveness of each addition.
Exactly. We're looking for a model that generalizes well, not just fits the training data. Computational cost also comes into play.
Absolutely. Let's say you have 100 features, and now you have hundreds of polynomial features. Your computations might take ages.
That's right. Computational expense is a key factor when choosing techniques. Feature selection helps limit the complexity.
It's a balancing act. Thanks, Sarah.
Anytime, Jane. It's really about using these tools wisely to understand the data better.
Sarah, you mentioned the potential for overfitting with polynomial features. Can you give a real-world example of how that might affect house prices?
Sure, imagine a model that learns a super complex relationship between house size and age, picking up on every tiny detail, like the specific type of paint used. While it might perfectly predict house prices for houses in the training data, it wouldn't generalize well to new houses. Maybe an entirely different color of paint is used, or an entirely new type of siding, and would give inaccurate predictions.
So, how do we prevent that?
We use regularization techniques, like ridge regression, or cross-validation to test different degrees of polynomials to see which works best on unseen data.
And what about this Boston housing data you mentioned?
It's an interesting data set. We added lots of polynomial features and interactions that increased the features from 13 to 105. That's a lot.
Whoa, 105 features. That's a lot of computation.
Precisely. It's a trade-off. If we use a kernel SVM, we don't need these extra features.
But wouldn't the SVM be more complex? How would we evaluate it?
Exactly. It's about finding the right balance. We use metrics like RMSE root mean squared error to compare models. We want a model that's accurate yet computationally efficient.
So, we don't just throw more features at the problem, but choose useful ones?
Exactly. It's all about using your knowledge about the data to choose the right techniques.
Sarah, would it be worth it to compare these methods quantitatively using the Boston housing dataset?
Absolutely. RMSE or MAE would give us a clear comparison of how well different models perform. We need the data to validate the models.
You're right. Let's look at the results.
The SVM may handle nonlinear relationships without explicitly transforming the data. But the explicit transformations in polynomial regression can often give insights that are easier to interpret.
So, what would your next steps be to see which method is best for a new model?
I'd calculate the RMSE for both methods and see which generalizes better to unseen data.
Sounds good.
Well, we'd have to check the actual error measures to see which is best in this case.
Absolutely. Sarah, you were saying polynomial features can really boost performance, but that wasn't the case for random forest, right?
Exactly. With Ridge, adding those interactions really helped the score. But random forest? Not so much.
Interesting. So, it seems feature engineering isn't one size fits all?
Absolutely. Random forest is very robust to the exact form of the features,
So, we need to evaluate feature interactions more carefully with different models?
Absolutely. It's not just about adding features. It's about seeing how those features play with the models themselves.
How about the order of scaling and transformations?
A good question. We often scale first, then engineer new features.
So, it might be important to experiment with different scaling methods, like min-max?
Exactly. You often see better performance when you put these steps in a specific order.
What about cross-validation? Wouldn't that tell us more about the real-world performance?
You're right. Cross-validation is essential for finding a model that generalizes well.
What does cross-validation do?
It helps us estimate how well a model will perform on unseen data, which is really what we care about in practice.
Wow, that sounds very important. And what if the polynomial features have an odd shape?
That's a great point. You might need to do additional transformation of those features. Transformations such as a log or exp are often helpful.
How do you even look for these?
Look at distributions of features, histograms, and correlation matrices.
So, are log or exp transforms necessary?
Not always, but sometimes you'll find that these can make a big difference for numerical stability in linear or neural models, particularly if a feature has skewed distributions.
Let's say we decide to add those interactions and transformations. How do we quantify how much those polynomial features help?
We use metrics like RMSE root mean squared error.
Okay. What's your next step in this model creation process?
I'd calculate the RMSE for both models, with and without the interactions, and compare, using cross-validation to make sure the results are reliable.
So, if polynomial features are better for some models but not others, how do we figure out what to do in practice?
We try different strategies and compare their performance using cross-validation and appropriate metrics.
Makes perfect sense. Great advice, Sarah.
Thanks.
Sarah, we've been talking about different ways to make features better for models. Now, what about changing the shape of the features themselves? Like taking the log of a value?
Yeah, that's a powerful tool. Sometimes features have this skewed distribution, especially if they represent counts, like how often a user logs in. These features are often heavily skewed to the right.
Why is that a problem?
Because linear models like Ridge are sensitive to the distribution of features. A skewed distribution can make it hard for those models to find the underlying relationship. They perform better if the data are, more normally distributed.
Oh, so how does the log transformation fix that?
The log transformation essentially shrinks the high values and expands the low ones. Think of it like squeezing a balloon. Some parts get tighter, other parts get more spread out. That makes it easier for a linear model to capture the trend.
So, We just blindly take the log?
No, visualizing that distribution helps tremendously. You see that before and after the transformation.
So, what would we look for?
Histograms, really. You want to see less asymmetry in the distribution after transformation. If there's still a large skewness to the right, try a different transformation like a square root.
Okay, so with count data, how often are these transformations valuable?
Very often. Imagine trying to predict customer churn based on how often they interact with your app.
Interesting.
That raw count data is often heavily skewed.
So how do we actually decide when this is the right approach?
Well, after the transformation, look at the new histogram and judge if it's closer to a normal distribution.
So, it's kind of like adjusting the volume on a feature.
Precisely. You're changing the volume levels.
So, is it okay to apply this log transformation without any other feature engineering?
It depends. Sometimes a transformation is all you need, but sometimes combining with feature engineering or scaling is beneficial too.
But isn't there a chance of introducing errors during transformation?
Absolutely. You need to be mindful of zero values. If you have zeros in your data, you can't take the log of 0, so you add 1 or a small constant to avoid undefined values.
What are other good options?
Square roots or even exponential transformations.
Okay, so we transform to improve the model's fit.
Precisely.
That's really helpful, Sarah. Thanks.
You're welcome.
Sarah, we've been looking at adjusting features like taking the log. Now what if we don't need all the features?
Exactly. Sometimes a model performs better with a smaller, more focused set of features.
How do we find the best features?
Well, one approach is univariate feature selection. We look at each feature individually and see how strongly it's related to our target variable.
Like correlation but more statistical?
Precisely. We use tests like ANOVA or in-regression statistical tests to find the strongest relationships.
So if a feature isn't statistically related to our target, we ditch it?
Yeah, we discard features with high p-values. Features that aren't significantly related to the target.
So, simpler models are often better?
Often. Fewer features mean less complexity and less chance of overfitting.
What's overfitting anyway?
Imagine a model that fits the training data too closely. It memorizes the training data and isn't good at generalizing to new, unseen data.
That's why we need to test, right?
Absolutely. We train on the training data, then test on separate, unseen data.
So, simpler is better, but you need to be cautious not to miss crucial information.
You got it. Feature selection is a balance.
Makes sense.
And in practice, you might try different selection methods to see what works best.
And does this apply across all models? Or are there different feature selections for different models?
Some models, like decision trees, often handle feature interactions on their own, so explicit selection might be less crucial. Linear models, however, can benefit more.
Okay, so feature selection isn't just for linear models?
No, it applies broadly, just that linear models' results are more directly affected by feature selection.
So, if we're trying to predict customer churn based on app usage, we might remove less relevant features?
Exactly. You might identify the app features directly relating to churn behavior, instead of using all features collected.
This is interesting.
Yeah, it's a critical step in building accurate, robust machine learning models.
Makes sense, Sarah. Thanks.
You're welcome.
Sarah, we talked about transforming features. Now let's drill down into choosing the right features.
Absolutely. This example uses select percentile, a method to automatically pick a percentage of the most relevant features.
So, it looks at each feature and scores its importance?
Precisely. It looks for the strongest statistical relationship to the target variable.
And how does it decide which are the best?
By calculating p-values from statistical tests, like ANOVA for classification. It removes features with high p-values, meaning they aren't likely to be connected.
So, it gets rid of noise effectively?
You bet. And the example shows that by removing less important features, even if some important ones get lost, performance can actually improve.
But how do we choose the percentage?
This is an important point. The example here uses 50%, but it's data dependent.
Does that mean we might need to try different percentages?
Exactly. You can't just pick one percentage and expect it to work for everything. You need to experiment.
Could another method be better?
There are others like Select K-Best, which selects a fixed number of top-ranked features. We should investigate and compare them.
It's a balancing act?
Absolutely. We want to keep features that improve performance but eliminate noise.
What are some other metrics we should consider?
Certainly. We should look at other metrics such as precision and recall, not just accuracy in the final assessment.
What about handling features with complex interactions?
This approach focuses on linear relationships. Potentially more complex strategies are needed for intricate feature interactions.
So 50% wasn't a magic number, huh?
Exactly. It's one possibility. Other techniques might find the optimal balance.
Thanks, Sarah.
You're welcome, Jane.
Sarah, building on our feature transformation chat, let's delve into model-based feature selection.
Absolutely, Jane. Univariate methods are helpful, but they miss out on intricate feature relationships.
So, how do models help us pick the best features?
Models like random forests can estimate feature importance.
How?
Trees build decision paths. Features used more often are more important.
Interesting. How does this help us?
We select features deemed most crucial by the model.
So, we're using a model to choose features for another model?
Precisely. Often not the same model but one that reveals importance.
Okay. Tell me more about Select from Model.
It filters features based on model-assigned importance above a threshold.
How do we pick this threshold?
Often the median or something similar.
Makes sense, Sarah. What about the random forest example?
It usually yields good results.
Does it always outperform univariate techniques?
Not always. It depends on the data.
So, what are some challenges with model-based selection?
Computational cost is sometimes high.
So, there's a trade-off?
Exactly. Powerful models like random forests often achieve better results, but at a computational expense.
What about other model types, like linear models?
Linear models also provide coefficients. We can use their magnitude as importance.
And could we try various models for feature selection?
Absolutely. Explore different models and compare results.
What about iterative feature selection, building or removing features incrementally?
That's another avenue, and it allows us to refine choices over time.
Any real-world use cases?
Say in medical imaging, finding key patterns.
Sarah, fascinating. Thanks for clarifying model-based selection.
You're welcome, Jane.
Sarah, now that we've looked at model-based feature selection, what about iterative approaches?
Yeah, we can use methods that refine feature selection step by step, like RFE.
Sounds more involved. How does it work?
It starts with all features, builds a model, and removes the least important one.
So, it keeps building models until only a fixed number is left.
Exactly. Think of it as progressively refining the feature set.
But, how does it measure feature importance?
The model used has to do that. It's often a model you trust.
So, using our random forest example, RFE retrains the forest many times, which, takes longer?
Yes, RFE is typically more computationally expensive than model-based selections.
More steps, more models?
Precisely a trade-off.
So, what's the benefit, then, of this added complexity?
Sometimes you get very good feature sets. Sometimes similar performance but at significantly less computational costs with different methods.
You're saying there's a potential for similar accuracy with fewer features.
Right. It might help for interpretability or speed.
What if the chosen model isn't very good?
Well, if the underlying model in RFE is weak, RFE might not be optimal.
So, it's not a panacea?
No, not always better. Data dependence is key.
Let's look at city bike data. What insight does feature selection give?
Clear diurnal patterns in bike rentals, but that's not a surprise.
How about selecting features for that?
RFE or model-based selection could pinpoint time-related features, making prediction easier.
So, RFE is a good option for specific cases?
Potentially. It's a tool, but you still need to carefully evaluate it.
You know what? It all seems very nuanced.
Absolutely, feature selection is not one size fits all.
What about tuning RFE? Are there specific parameters to optimize?
Yes, like the number of features to select or hyperparameters of the model inside RFE.
This is insightful. Thanks for your expert perspective, Sarah.
Anytime, Jane.
Sarah, now that we've tackled feature selection in general, let's dive into something specific, time series data.
Right. When we have data that's ordered over time like city bike rentals, we have to think carefully about how we split our data.
How so?
We want to use all data up until a specific point as training, and the rest for testing.
So, future data shouldn't influence past data. Makes sense.
Exactly. We're trying to predict the future based on what we know about the past.
What about hour and day of the week? Are those good features for predicting rentals?
Absolutely. But we have to consider how different models interpret integers.
Linear models treat them differently than nonlinear models, right?
Exactly. A linear model might see them as sequential, so a later hour or day of the week is bigger than earlier values. But that's not what we want.
So, how do we handle it?
One-hot encoding. We convert those integers into a series of binary features, representing each category.
Makes things easier for linear models. But a linear model failed in the example.
Because the pattern is more complex than a simple linear trend in the time series data. It's not just that later is more, there are cycles.
Like cycles in day-to-day patterns, week-to-week patterns.
Right. One-hot encoding helps the linear model understand those patterns better.
So, what's the takeaway here?
Feature selection for time series data requires careful considerations for data splitting and feature encoding techniques. Linear models require special treatment of integer-based time series data.
Thanks, Sarah. Learning so much. Sarah, we've explored the critical role of feature engineering, especially when dealing with time series data.
Exactly. We saw how the right representation of data, like using one-hot encoding, makes a massive difference for specific models.
So, now that we're past the feature engineering phase, what's the next key step in building a solid machine learning model?
Model evaluation and parameter tuning. Picking the right model for the job is often as important, if not more important than sophisticated feature engineering. It's about matching the tool to the task.
Oh, interesting. Can you give me an example?
Sure. Imagine you're trying to predict customer churn. A simple linear model might not be sufficient. You need something more sophisticated.
Like what?
Maybe a random forest or a support vector machine. They can model much more complex relationships.
How do we choose?
Well, it depends entirely on the data and the desired outcome. Does accuracy matter more than interpretability?
So, some models can be much more accurate, but it's much harder to interpret why they made a certain prediction.
Exactly. Often it's about striking a balance.
Can you imagine a scenario where we have limited time and data?
Absolutely. With limited data, you might have to choose a simpler, more interpretable model. You want a model that you can easily understand.
So, we have to think practically.
Yes. It's not just about the raw numbers. It's about understanding the trade-offs between complexity, accuracy, and interpretability. This is where experience and domain expertise come in.
You're making it sound so much easier to do.
Well, a good machine learning practitioner knows that picking the model and the features to use is often the most important factor.
Makes sense.
And keep in mind that model evaluation metrics are crucial.
Absolutely.
They provide a quantitative way to measure model performance, helping you decide if it's meeting your project's goals. And this changes based on the context. If it's a business model, you care about precision, not just accuracy.
That's excellent insight.
Thank you.
Sarah, your insights are truly invaluable. This has been an incredible journey.
Thank you, Jane. It's been great talking with you.
I feel like we've scratched the surface of a vast ocean of possibilities.
Precisely.
So, for our listeners, let's continue this discussion. Subscribe to our podcast to stay tuned for more episodes. We'll delve deeper into model evaluation and parameter tuning in future episodes.
Agreed. We can't wait to see you in our next episode.
Goodbye, listeners, and thanks for joining us.
Goodbye.